Alright, this video is on phase change diagrams, okay, also known as heating and cooling curves. This would be an example of a heating and cooling curve. If you go to the table of contents on the website, it'll say heating curve or it'll say phase change diagram. There's a link there. Go ahead and click on it. It'll download this. You can print this out. This is all you need to write. You write this right here and we can make annotations and we'll work out a problem. But if you print this out, then this should be the only paper you need. If you don't have a printer, you can just copy down the chart or the graph. It's not that difficult. Okay? So what this phase change diagram is showing right here is on the x-axis, I am adding heat to the system. Okay, so as I'm going across the x-axis, heat is being added to the system, and my y-axis would be temperature. Okay, so just so we can see that, right now, when I am at this stage right here, okay, well, I got to think, well, am I undergoing a change in temperature or am I not? Well, if you notice, when I'm adding heat, my temperature is going up along this slope, which means I am not undergoing a phase change because my temperature is changing. Okay? However, once I get to this point right here, okay, and I've started to pretty much I've started to melt, right? I'm going from a solid to a solid slash liquid, which means at this point along that red line right there, I have liquid and solid, okay? At the same, kind of within the system, there's a liquid component and a solid component of the same piece of, or the same same molecule. If this was water, this point right here is 0 degrees Celsius, okay? Because that is the melting point or freezing point, same thing, of water. Okay. When I go back up my line and I'm noticing a temperature increase again, that must mean I am not undergoing a phase change because my temperature is changing. So this point, okay, from between I guess the new blue line, you could say, that is where we're heating up water. As I am adding heat, my temperature is going up, so my heat or my temperature value is going to remain is not going to remain constant because I'm not undergoing a phase change. Okay. Next step is with this point right here where I have a liquid and a gas. So the state of matter is both liquid and gas at this stage. And of course, this is, if this is water, which that's the model we're using, that's 100 degrees Celsius because that's the boiling point slash condensation point of water. Okay? And then once all of the liquid has been converted into a gas, then I go back to a temperature change when I increase heat. So blue, I have temperature change, okay? With red, I have no temperature change, which is equal to a phase change, right? Okay, so that's how you read a heating curve. Okay, so I add heat as I go across the x-axis. I increase temperature as I go up the y-axis. When I undergo a phase change, like I am in the red spaces, in the red lines, I am not having a change in temperature. If I have my blue lines, as I increase heat, my temperature changes, which means that there is no phase change going on. Okay. Now the different types, the heating and cooling, it's like I said, it's the same curve. It's just based on what direction you're going with it. Okay. If I am heating, like this heating curve, okay, that means I'm putting heat into the system. That's an endothermic process. So the process, like I said, if I had blue right here, that's not blue. This is blue. I have blue right here. Well, if I wanted to find out how much energy was being transferred at that step, well, since I have a change in temperature, I'm going to use MC delta T. When I'm actually undergoing the melting, right, I'm going to use delta H of fusion. When I'm heating up the water, I'm going to use MC delta T because my temperature is changing. When I go here and I'm boiling the water, delta H of vaporization. And lastly, when I'm heating up the gas, that would be MC delta T again because I'm going to have a change in temperature. All right? So you're thinking, well, what's the difference between, say, this curve and a cooling curve? Well, a cooling curve is the exact same thing, but the energy is going out of the system. So I'm having energy leave the system. And honestly, it's all the same stuff other than this delta H, and this delta H, and this delta H, this delta H, and this delta H are all negative because it's an exothermic process. So it's really negative delta H, negative delta H, negative delta H, negative delta H, and negative delta H. Okay, but the process of finding the energy is still the same. It's just the sign is different because I'm cooling it down instead of warming it up, meaning I am taking heat out of the system versus putting it into the system like I did with this diagram. And where I have my arrow pointing up. Okay? So let's go ahead and determine how do I solve a heating curve problem. Well, what I need to do is I need to add up all of the delta H values from each step along the curve to determine the total energy. So for example, if I'm going a certain mass of an object or a mass of water, and I want to go from ice to gas, and I want to know how much energy it takes to take this mass of ice into this mass of gas. Well, there's 5 different processes there. One, I have to, so if I have my solid, say my solid's at negative 5 degrees Celsius. Okay, well here I have to raise the temperature of the ice to the melting point, which would be 0 degrees. Well, if I'm going from negative 5 degrees Celsius to 0 degrees Celsius, well, that's a change in temperature. So I need to use MC delta T. Delta H of melting, well, it's a phase change, so there is no temperature change, which means I am not going to use MC delta T. I will use delta H of fusion. Right? Delta H fusion. If I'm going from the liquid to the boiling point, so now that I've melted all of my solid and it's a liquid, okay, this delta H, I need to go to the boiling point, which would be from 0 degrees Celsius to 100 degrees Celsius. Hey, look, I have a temperature change, which means I'm going to use MC delta T. Right? And here, I'll also use MC delta T. Next step, boiling. Boiling is a phase change. There's no temperature change, but it's a phase change where gases are involved. Therefore, I'm going to use delta H of vaporization for water. And then lastly, I need to say my ice was at -5, but my gas was at 200. Okay? I need to raise the temperature of my gas from 100 degrees Celsius, which is the beginning of the gas phase, to 200 degrees Celsius. Well, hey, look, that's a temperature change. I'll use MC delta T to determine that delta H. And then I would take this delta H plus this delta H plus this delta H plus this delta H and this delta H to get my total delta H. And we're going to do a problem like that. Okay? Now, when it comes to a cooling curve problem, it's the same process. It's the same equations to use. The values may be different as far as the temperatures, okay? But it's the same process because all I would be doing is my delta H's would all be negative because when I cool things down, like I said, that's an exothermic process. Okay, so again, this gas to boiling point, that means I have a gas and I'm cooling it down to get to the boiling point so it'll condense. Okay, well, that's a temperature change, MC delta T. Delta H of condensation, that is a phase change. And it's a phase change with gas, delta H of vaporization. Now I'm going from liquid to boiling point. This would be a change in temperature, MC delta T. Freezing is a phase change, delta H of fusion, because it's dealing with a gas. And then lastly, cooling the solid down. So understand that I can cool like an ice cube, all ice cubes are not all the same temperature. I can cool ice lower than 0 degrees Celsius. What if I had it at negative 20? Right? I can still do that. But since I am cooling the temperature down, or cooling the solid down and lowering the temperature of it, I would use MC delta T because I'm going to have a change in temperature. But I would still add up all those negative numbers that you would get, and I would still get a total negative number. Remember, the negative number has nothing to do with the value of the number. It has to do with the direction of the energy. So, let's go ahead and do a problem. Calculate the energy required to change the temperature of 8.5 grams of ice from negative 25 degrees Celsius to 105 degrees Celsius, which means here I'm ice, and here I'm going to be steam, which means somewhere in the middle I need to have been liquid at some point. And in this process, I need to heat up my ice to get it to melt, and then I need to make it so I make it into a liquid, right? And then I need to raise the temperature of the liquid to the point where I can boil it. And then once I do, I need to boil it to the steam. And then I need to increase the steam's temperature by another 5 degrees because the boiling point is 5 degrees Celsius. So let's go ahead and look at our values. Okay, if you notice, I have kilojoules here and I have joules here. All right. Just for the fun of it, I'm going to convert these values into joules once I solve for kilojoules. Okay, so I'm eventually going to convert that to joules, and then I will add this joule, and then use that joule, and this joule to get the total amount of energy. Okay, so here's my heating curve. My first step is going to be, remember, I'm going from ice at what, negative 25 to steam at 105 degrees Celsius. So there's 5 different steps here. I'm going to do all 5 of these steps. The first step is I need to raise the ice from 0 degrees, or excuse me, negative 25 degrees, wow, can't write today, negative 25 degrees Celsius to 0 degrees Celsius, because that's the temperature that it takes to get to melting, okay, because that's the melting point. So I do that. I have a change in temperature right here. So delta H is going to equal MC delta T. Well, delta H is going to equal the mass. The mass was 8.5 grams. The heat capacity of ice is 2.0 joules per gram degrees Celsius. If you have any questions on how I got that value, you need to go back and look at your heat capacity worksheet. Okay, questions 7 and 8. And then I went from 25 degrees Celsius to 0 degrees Celsius, which means I had a change in temperature of 25 degrees Celsius. That cancels out. Grams cancel out. I have joules. When I do my work, I end up with 425 joules, but I don't want 425 joules because I need to have proper sig figs, so my final answer is 430 joules because of those 2 sig figs, or those 2 sig figs, or those 2 sig figs, since they're all significant. Okay, so my first step, and I'm going to go ahead and keep this as a running count, okay, going from this point here to this point here was 430 joules. All right? So that's step 1 of 5. Step 2 is I need to, once I have the temperature up to melting, now I need to melt my ice. Well, remember, melting ice does not have a temperature change, as you can see with the point between here and here. There's no temperature change, which means if I'm doing no temperature change, then delta H is equal to the delta H of fusion times the moles, right, of however many moles of water I have. So I'm going to go with 8.5 grams, which is what I have, of ice. And then this is the same problem that we did in class. Okay, 18.02 grams of ice to 1 mole of ice. And then 1 mole of ice is 6.02 kilojoules. And then lastly, I'm going to go 1,000 joules is equal to 1 kilojoule. So kilojoules cancel out, moles of ice cancel out, grams of ice cancel out. I'm left with joules. My answer is going to be 2,800 joules, which means from point B here to point B here, that's going to be an additional 2,800 joules. Okay, so let's do another step. Step 2 of 5, done. Now I'm going to heat up the liquid because I've melted my ice now. Now it's all liquid. Now I need to heat it up to the melting point, which is 100 degrees Celsius, because that's the melting point of water. So since I have a temperature change, delta H is going to equal MC delta T. Delta H is going to equal 8.5 grams times 4.184 joules per gram degrees Celsius times the change of temperature. I'm going from 0 to 100. So that's 100 degrees Celsius. Okay, degrees Celsius cancels out, grams cancel out. I have joules. When I do my work with my sig figs, my final answer ends up being 35,000 divided by 18.02. So with 2 sig figs, 19,000 joules. Oops, wrong one. Okay. Wrong notes. Let's get rid of that. So if I go 8.5 times 4.184 joules times 100, I'm going to end up with 3556.4 joules, which is, with sig figs, 3,600 joules. Okay, so that means from this point right here to this point right here is 3,600 joules. All right, now step 3 of 4 done, 3 of 5 done. Now I'm going to melt, or excuse me, I'm going to boil all this water and make it steam, which it's phase change, which means I have no change in temperature. So delta H is equal to the delta H of vaporization times the moles. So I'm going to use dimensional analysis to do that. Okay, so I'm going to go 8.5 grams. It's always going to be 8.5, right? I'm not going to destroy matter. 8.5 grams of steam. Again, this is just like we did in class, over 1. Okay, 18.02 grams of steam for every 1 mole of steam. And then for every 1 mole of steam, I have 40.7 kilojoules. And then every 1 kilojoule is 1,000 joules. And that's an exact number. Remember that 1,000 is an exact number, so we would not have a sig fig issue there. Kilojoules cancels out, moles of steam cancel out, grams of steam cancel out. I'm left with joules, and this was my original blunder. If I do that math, I end up with 350,000 with the sig figs divided by 18.02, and my final answer is 19,000 joules. So that means from here to here, 19,000 joules. Step 4 or 5, done. So last little bit is I need to go from the steam that's at 0 degrees Celsius to the gas that is at 105 degrees Celsius. So I'm going to go from here, all right? I'm getting some pin working here. Well, having some pin issues, all right, there. So last step is I have a change in temperature because I'm just going to increase the heat of the gas. So the vapor is going to go delta H equals MC delta T. Delta H equals 8.5 grams times the heat capacity of steam is 2.0 joules per gram degrees Celsius. Change of temperature, a mere 5 degrees. Degrees Celsius cancels out. Grams cancel out. I'm left with joules. my final answer here is going to be 85 joules, a mere 85 joules. So here is 85 joules. So, final step, I add all those numbers together. So I add 85 joules plus 19,000 joules plus 3,600 joules plus 2,800 joules and 430 joules, and my final answer ends up being 26,000 when you take in a sig figs, because there's only going to be 2 sig figs, joules, or 26 kilojoules. This is my final answer to the problem. Yes, you will have one of these on your test, and no, you will not have more than one of them. Okay, because they are, as you can tell with the length of this video, fairly long problems. Okay, so if you have any questions, send me an email or ask me in class tomorrow.